Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the concept of Bernoulli's equation for the real fluid application, and also we'll solve a problem related to that. So in the last lecture, we have discussed the Euler's equation, and also we have derived the Bernoulli's equation from the Euler's equation. Okay, and there I have informed that the Bernoulli's equation, what is considered, that having some assumptions we have considered, like the fluid need to be incompressible, the fluid considered as a steady flow, fluid flow will be steady flow, and the fluid is considered as the ideal fluid. Okay, now for the ideal fluid condition we have considered and we have derived that Bernoulli's equation. Now when we'll consider the real fluid, when there is a real fluid is there and there is a flow suppose in a pipe, and in that case what will happen? Now we need to consider the fluid is having some viscosity. Okay, because in the previous ideal fluid condition the fluid is having that fluid is inviscid, that means no viscosity is there. But in real fluid condition there should be a viscosity in the fluid. And when we are considering this one, now when there is a flow will be there in the pipe, correct? So in the flow we can consider some kind of section 1 and section 2, and there we have derived that Bernoulli's equation for that. Okay, now the next condition is if there is a real fluid considered. Okay, if you have considered the real fluid, then what will be the equation of Bernoulli's for that? Because previously we have derived the Bernoulli's equation for ideal fluid, correct? Now what will you do if you consider the real fluid? Then what is the concept that the Bernoulli's equation which was derived for the ideal fluid, okay, that is inviscid or non-viscous. So you can say there is no friction in that, so that is frictionless. But if you consider the real fluid, then these are viscous. Fluid is there, and that means when the fluid will be the flows in the pipe, there offers one resistance to that fluid flow. So that means there is some friction is there, and we need to consider some friction. Okay, so there is some losses will be there when the pipe, when the water liquid will be flows, there is some losses will be there due to this friction. Okay, and then if you apply the Bernoulli's equation, okay, suppose this is section 1 and this is section 1 and this is section 2. So when the fluid flows from section 1 to section 2, so there is some losses will be there in this zone, in this layer and this layer, okay, near to the surface layer of the pipe. So that is some losses can be considered during that. So now the Bernoulli's equation, if we apply for the real fluid between the point 1 and point 2, we can write, we know the equation, that is P1 by rho g and plus V1 square by 2g plus Z1 equal to, I can write P2 by rho g, and this is V2 square by 2g plus Z2. Now this is the Bernoulli's equation normal is there. As I told you that this is a real fluid, so we need to consider some losses here between section 1 and section 2. So that losses will be called as a HL, and this HL is actually known as the loss of energy, between point 1 and point 2. Okay, remaining terms we have as usual. As I told you, this is your pressure head, and this is velocity head, this is potential head. Okay, these three terms at this layer 1, and similarly at layer 2 again pressure head and velocity head and potential head. So when the flows will be there in this between these two layer, it's in this two zone, so there is some losses of energy occurred there, then that is indicated in HL. Okay, and see the flows we have considered from starting here. That's why after moving this much distance of this water from here to here, then what are the losses happened from here to here, that can be identified here. So what is the energy, total energy was there, that should be equal at this point. So the losses happened between this plus this energy, then it will get the same thing here. That's why the loss of energy was added in this side, in the second part of this. Okay, so I hope you understand this concept. Very simple only. What we have discussed previously, same thing. Just I have added a losses in that particular equation, and remaining all are same thing is there. Now related to this, we'll solve one problem related to that, and the same equation is going to apply like one of this equation, but we need to consider the real field condition. Okay, so the question is given here. A pipeline carrying oil of specific gravity 0.87. So here the data given, we can write the specific gravity equal to 0.87. Now here the liquid is taken, or the fluid is taken, oil, and changes its diameter from 200 millimeter to 200 millimeter diameter at a position A to 500 millimeter diameter at a position B. That means the pipe which is carrying this oil, okay, it is having a shape of I can say some divergent type is there, suppose. Okay, so here it is 200 is there, 200 meter diameter, and here at this other end, that is at B point, that is 500. This is suppose A point, but only given 200 millimeter at position A. That means at position A, this is diameter, and 500 diameter at position B, which is 4 meters at a higher level. Okay, so this position, okay, from this datum line, suppose this is our datum line is there. So from here, from this point to like this height should be 4 meter. Okay, that means in such a way we need to keep the pipe. Yeah, next is, if the pressure at A and B are 9.81 Newton per centimeter square, 5.886 Newton per centimeter respectively, then the discharge is 200 liter per second. So here the pressure 1 PA given, and here it is PB given, and Q given the flow. Determine the loss of head. See, now the loss of head and the direction of the flow. So from the symbol, like from the sign of this value, we can identify from which direction to which direction the liquid is flowing, and we need to also find out the head loss. That means HL we need to calculate it. Okay, so let me draw a diagram properly here. So suppose this is the datum line is there, and the pipe which is considered, we need to first draw this center line of this pipe, so that we can draw here like this, and this will be, it will be in the divergent mode, so that because the diameters are given in differently. So here at inlet condition, the diameter is given 200 millimeter, and at this outlet in a sense at B point, that is another one point. And why I've drawn this one, because the other part of this B part, that is situated with a height of this height is given 4 meter from the base point, or from the datum line we can say. Okay, so these things we can mark it here. This is the B point, and I can mark it here 500. This is diameter, so this is DB, and this is DA I can write, and this is 4 meter, and this is situated on the datum line itself, because there is no point is given, just only this point only it is having a height. And next is PA is given here at this point. What is the pressure level? 9.81, and this is PB at this B point, that is 5.886 Newton per centimeter square. Okay, now we need to find Q. The value of Q is given 200 liter per second. So this one we can convert into meter cube per second. So that will be this is 0.2, but you just divide by 1000, then you will get, so that is nothing but 0.2 meter cube per second. Okay, so these are the value is given in this problem. Now what we need to do, remaining things we can calculate. First DA given, so you find out the area of this at A point, that means area at A point, pi by 4 d square, because circular part is there. So pi by 4 ds square. So it is here I have taken capital D. Here also you can write capital D, or if you want to mention small d, we can mention the small d also. So this is pi by 4 into dA. That means here it is given 200 millimeter. We can convert it into meter. So that will be 0.2. So this is 0.2 into 0.2. Okay. So it will be cancelled and 3.14 will get it. See, 0.4, because this is 2.2.2. If you multiply it, 0.04 will be there, and 4 will be cancelled, and so suppose we'll get 0.01. Okay, 0.01 and into 3.14. So we'll get here 0. This will be 0.314. This is area, meter square. Similarly, you can calculate the area at the B point. These are the very simple things we can calculate immediately. Okay. After that, we'll see what is the next things need to be calculated, because we know the formula, Bernoulli's equation formula. So based on that, all this value required. So again, pi by 4 into d square. Again here 0.5 into 0.5. So for this 0.5, that is 0.25 will be there. 0.25 into 3.14. So 7.8 point something. So divided by 4, we'll get it, near about 1.9 something will get it here. So 1.9, we will calculate it better. Calculator. Yeah. 0.5 into 0.5 into 3.14 divided by 4. 0.196, 0.19625, which is meter square. Okay. So these are the values are there. So this is all about area. Now next, okay, just to remind this data what is given. Next, what I'll do, I'll go for this. We know that we can write Q given, Q equal to, we know from that continuity equation equal to, that is AV. So here A1 V1 or A2 V2 also we can write. So for at this A section or at the A point, I can write what we need to calculate. We need to calculate the V point, V velocity at the A point, suppose. So here you can write area A, and this is velocity A, and this is Q, that is 0.2 divided by this area is 0.0314, I hope. Yeah. So if you solve this, what will get here? So let's divide this 0.2 divided by 0.0314, 6.36, 6.369 meter per second. Okay. Similarly, we can calculate the the velocity V, VV at this point. Correct. So similarly, in the same formula, I can write VV equal to, again, 0.2 divided by 0.196. So that again it will be calculated 0.2 divided by 0.196, 1.02, 1.02 meter per second. So these are the value what I got there. Okay. Now the next thing is what we will do, because we know that Bernoulli's equation, what I told you here. See, this is the part at the section 1, this is the part of the section 2, and the losses between them. So this one we can consider the energy, total energy at A point, this is total energy at B point, and the losses here. So what I'll do, as per the Bernoulli's equation, let's find out the total energy at the A point. So we can write, this is PA by rho g, and this is VA square by 2g, and this is Z1. So I can write the value here P1 or PA given how much, 9.89. So here it is given centimeter square, we can convert it to meter. So we can write 9.81 into 10 to the power 4. Again, we need to calculate rho. Rho value, how much is given? Rho not given. Here it is given specific gravity 0.87. So that can be converted into rho. So rho will be, density will be the specific gravity into the density of the standard fluid, that is water. So 1000 if you multiply, then we'll get 870. So density will be 870 into again 9.81. Okay, plus Vs square. Vs square already is given here, 6.37 square we can write, divided by 2 into G. So again same thing, plus Z1. Z1 or ZA, this is Z1 is ZA. ZA is nothing but 0 because it is situated at the datum line itself. Okay, so we need to solve this and we need to identify the value here. So I can write this value. Let's, yeah, so 9.81 will be cancelled. So 10 to the power 4 divided by 870. So what I can do, divided by 870, 11.4, 11.49, that is one value. 11.49 plus, see this 9.81 cancel, this is 10 to the power 4, that means 10,000 divided by 878. And next one is 6.37 into 6.37 divided by 2 into 9.81. 9.81 into 2, that will be 19.62 divided by 19.62. So we'll get the value of 2.068. 2.068. So here it is 0. So finally we'll get some 13.5. 13.56 something will get, that is the meter. This is EA. Similarly, we can find out the total energy at the B point. So same formula again, we need to write PB by rho G plus VB square by 2G plus ZB. So here again, we need to see the pressure value, how much? 5.88. So that is, again we can convert into meter. Yeah, 10 to the power 4. Now here again rho G, rho again 870 into 9.81 plus VB 1.02. So 1.02 square divided by again 2G, 2 into 9.81. Now here again we will get the value of ZB. ZB is already given 4 meter height, so we can write 4. Now again we need to solve this all this value, and let's see what we'll get here. So 5.88 into 10,000 divided by 870 divided by 9.81. 6.88 or 6.89. This is pressure head. Now again velocity head, you can calculate 1.02 square. So 1.02 into 1.02 divided by 19.62. So 0.053. 0.053 plus 4. If you add all these things, 6, 4, 10, 10.89, then it will become 10 point, add up this 10.948 something will come. Okay, this is meter. Now we got these two values. Now we'll put this value in this equation, Bernoulli's equation. So we know that here we can write head loss HL equal to 13.56 minus 10.948. 10.948, correct. So we'll get the value some 2.6 something like that. That is the head loss. Yeah, this is the final answer of this head loss. Now here I can say the EA, the energy at the A point, that is 13.6, okay, and energy at the B point, that is 10.948. So the EA is more than the EB point, and we can say that the flow is taking place, this flow is taking place from here to here, A to B, because the energy is more here and the energy is less here. So we can say the flow is taking place from A point to B point, because here we need to find out the direction of the flow. So same thing, the flow is taking place from here to A to B point. And the loss of head, as per this formula, loss of head is equal to 2.6 meter. I hope you understand this problem and this concept of real fluid. If you are having any kind of query regarding this, you can give a comment on the comment box. Thank you all.